Welcome to qnawire.
Problem 129 asks to find the centroid of a volume generated by revolving this portion of the sine curve shown in the diagram and revolving it around the y-axis. Now, since it's being revolved around the y-axis, just looking at symmetry, we see that the centroid in the x direction and z direction are going to be equal to 0 because it's going to be symmetrical about those axes. Now, we'll have to find the centroid in the y direction by using this equation where the centroid in the y direction times its total volume is equal to the integral of the centroid of the differential element dv. And our differential element, they give us a hint on how to find this by using a cylindrical shell. So if we draw out what it looks like when it's revolved around the y-axis, it looks a little bit like this. And our differential element will be a cylindrical shell that encircles the volume. Where we have a radius out to the start of this cylindrical shell, and then we have the differential radius that will integrate across for each shell, adding up to the entire volume. And then we have our differential element that we'll need in the y direction will be equal to 1/2 of y. And the differential volume of this shell is going to be equal to 2 pi r, or the circumference, times y, its height, I suppose you could call it, on the on this volume, times dr. Now we don't know what y is, so we'll need to find that in terms of things we do know. And luckily we are given an equation of the line where y is equal to b times sine pi x over 2a. So we can plug that into our differential volume. And now we can solve for the volume that we'll need to plug into our equation for the centroid. The volume is equal to the integral of dv, and this is going to be integral from 0 to 2a, which is the length of this volume, this object. So we can just plug in the dv that we found. We also need to get rid of x in this equation. And we can just plug in r for x because r is along the x-axis. So now it's all in terms of r. To perform this integral, we'll do integral by parts, where I'll select RD for, which would make du dr, and then for v, or rather for dv, I'll use sine pi r over 2a dr. So then v would be negative 2a over pi cosine pi r over 2a. Now for integration by parts, the integral is going to be equal to uv minus the integral of v du. So you can multiply u times v and get this. From 0 to 2a. Then we can subtract the integral of v du. And plugging in 0 to 2a for this first part, you get negative 2a over pi times a negative 2a and taking the integral of the right part of this equation, you get a 4a squared over pi squared sine pi r over 2a from 0 to 2a. And plugging in 0 through 2a, we get that that volume is equal to 5.454 a squared b. And the last part we'll need for our centroid equation, it will be the integral of the centroid of the differential element, which will also be integrated from 0 to 2a. And we know that the differential element is 1/2 y, and we have an equation for y for the equation of the line, so we can just take 1/2 the equation of the line, or 1/2 b sine pi r over 2a. Then we multiply that by dv, which we found earlier, to be 2 pi br sine of pi r over 2a dr. Simplifying, this was equal to pi b squared integral from 0 to 2a of r sine squared pi r over 2a dr. And again, we'll use integration by parts. Select R for U, which is makes du equal to dr. And the sine squared pi r over 2a dr for dv. Because then we can integrate that to get v, which is r over 2 minus sine of pi r over a divided by 2 pi over a. Now we can plug those in. And this is u times v from 0 to 2a, and then we subtract the integral of v du. And simplifying, we get pi b squared times a 2a times 2a over 2 minus a squared over 2 minus the solved integral, which is r squared over 4 plus a squared over 2 pi squared cosine pi r over a from 0 to 2a. Now just plugging in 0 and 2a, we can solve and simplify to get that the integral of the differential element is equal to 2.038 a squared b squared. And now we know everything to plug back into our original equation of the centroid times the volume is equal to the integral of the centroid of the differential element. We found the volume first to be 5.454 a squared b. You can set that equal to differential element we just solved for. We get that the centroid in the y direction is equal to